Hi everyone. Uh, so I'm going to talk about a new topic which is called emerging paradigms for security of consumer electronic systems. So as we know, uh, IoTs have become a buzzword these days. It's very common. So in an IoT, the device features are typically uh, comprises of the following. These are mostly battery operated. They are small in size and they transmit the information of the data through wireless sensor nodes. They also use crypto algorithms for secure communication and which are usually lightweight in nature. And as quite evident, we always have a trade off between battery life and power consumption. There are several challenges in the embedded and IoT devices. Two of the most major challenges that we see in an IoT device is energy efficiency and security. Since these are battery operated devices, they have to be energy efficient by nature, and they are also vulnerable to different sort of hardware and malware attacks such as power analysis, IC piracy, IC counterfeiting, hardware trojans. So these sort of cyber attacks are a threat to the reliability, safety, consumers' personal information, and piracy as well as cloning of the IP cores. Now let me introduce you to the formal definition of what is hardware security and IP core protection. So as the name suggests, it's a security mechanism and it's an emerging area of research for consumer electronics community and industry that focuses on protecting designs against standard threats such as reverse engineering, counterfeiting, forgery, and malicious hardware modification. So, the hardware security is broadly classified into two types. The first is called authentication based approaches, and the second is obfuscation based approaches. In the second type of hardware security approach, which is obfuscation, which is sort of an method to obfuscate the design into a different form or used to encrypt the circuit, can again be further divided into two categories, which is called structural obfuscation and second is functional obfuscation or logic locking. Structural obfuscation transforms a design into a one structure that is functionally equivalent to the original but is significantly more difficult to reverse engineer, while the second one is an active form of protection that locks the design through a secret key. Now, there are different approaches for hardware security and IP protection. If you talk about the threats to an IP core, there could be different types of threats, starting from false claim of ownership, which is also known as ownership abuse. There could be a possibility of piracy, Trojan insertion, and several others. The ways to counter or defend against these mechanisms could include digital watermarking for false claim of ownership, or computational forensic engineering, which is another way to resolve an IP core ownership resolution conflict without the use of signature. Piracy can be countered using IP metering, while Trojan insertion can be countered using logic or structural obfuscation. Now, let us look into an example of a DSP core in a consumer electronics system. So, as seen in this figure, it's an example of an MP3 encoder chain that uses several DSP blocks or DSP macro operators inside its algorithm, starting from the filter bank to the Fourier transformation to the MDCT, which is called modified discrete cosine transformation. The audio data, which is a PCM signal, is sent to the filter bank, which is further divided into different subbands and sent or fed into the MDCT block. After the Fourier transform, it passes to the psychoacoustic model, and then both the outputs from the MDCT and the psychoacoustic model is fed into the quantization and encoding block, which is responsible for compression. And after passing through the Huffman encoding compression, the final data stream is produced. So as you could see, a C system has several DSP blocks as a part of the major algorithms such as MP3. Now let us look into one of the recent methods that has performed structural obfuscation of DSP circuits or DSP hardware used in C systems. So the flow is as follows. It starts with the input, which is in the form of the application of the DSP, which could be in the form of an intermediate representation like control data flow graph. Then the first step checks for redundant operation elimination. If yes, then it passes to the next block, which is logical transformation. If yes, it passes to the next block, which is tree height transformation. If yes, then it passes through the next phase, which is resource transformation. And then it creates an obfuscated CDFG of the DSP core. Now this obfuscated CDFG, once it passes through the high level synthesis framework, will produce an obfuscated, structurally obfuscated or camouflaged RTL circuit of the DSP application, in contrast to the original one, which has not been through this structural transformation process. So once we have the obfuscated CDFG, in order to create a fault secure design, it could be passed through a dual modular redundant block to create a DMR design, followed by some fault security scheduling rules and fault security hardware reallocation rules, followed by reconfiguring mux and demuxes using cut insertion, which allows you to share the resources in a different way, resulting into reconfiguration of the mux demuxes, which are the switches. And finally, we have an obfuscated fault secured DSP design. Structures look vastly different in terms of the structural interconnections and interconnectivity. However, the application or the functionality is preserved. There is another type of IP protection mechanism which is called digital watermarking, and I had made a video on IP watermarking sometime back, which interested people can refer to for more information. So in short, I'll speak about the watermarking and an algorithm that has been recently proposed to solve the problem of IP protection in terms of the false claim of ownership. So as we know, watermarking has a widespread use in many disciplines such as currency, bank checks, multimedia content, etc. So it's a natural way to think that watermarking could be deployed for hardware software IP protection as well. Now, embedding a robust watermark at higher levels of abstraction such as behavioral or algorithmic level, which is especially very important for applications or complex designs such as DSPs, it can serve as a line of defense against attacks, secondly for nullifying the false claim of ownership, and as well as protecting the value of a reusable IP core. The four major properties or four major desirable properties of a watermark that needs to be implanted in a DSP or an IP must be as follows. It must be able to minimize the embedding cost. It should be resilient against attacks. It should have fault tolerance property, as well as it should have lesser watermark creation time and signature detection time. Previous slide shown here. So we have the encoded meaning of each of those variables. So these meanings are used to decode those respective variables in that particular signature. So I'll get back to that slide again. In the previous slide here, so the same table is shown here in the middle. Now V2 and V6, as we see, are present in the green register. So these needs to be changed so that they are assigned to different or distinct register assigns. So what we do right now is we kind of swap the value of V6 to a different register now, and we have V6 now allocated to yellow, and in place of V6 we have V7 and V10 allocated to green register. Correspondingly, the CIG on the bottom changes in color. So now we see that V6 has been assigned to yellow, which was previously green, while V7 and V10 is now assigned to green, which was previously yellow. Okay, so this shows that the modified CIG has now taken into consideration these signature based watermarking constraints, which is here. So the attack block here could be a key sensitization based attack, which we are going to talk about now. So key sensitization based attack means to sensitize the value of the key to the output by just controlling the primary inputs. There are different types of key sensitization based attacks. The first is called isolated key gates based attack, which tells that if there is no path between K1 and K2, then they are isolated key gates. An attacker can sensitize the value of K1 as 0 to the output O1 by applying the following bit pattern, which is 1 0 0 and 3 don't cares in the input condition. Similarly, in the run-off key gates, what can happen is if a set of key gates are connected in a back-to-back fashion, it increases the possible correct key combination. So in this case, both 0 1 and 1 0 are the correct keys. And finally, we have something called concurrently mutable key gates. If two or more key gates converges but have no common path between them, then by applying a certain input value, which is in this case I6 equals to 0, it can mute the other key, which is K2. As a result of which, the value of K1 can be sensitized at the output O1. Some other types of cybersecurity attack includes IP piracy and Trojan attacks. So IP piracy attacks and Trojan insertion attacks aims to identify correct key to understand functionality of an IP. So the Trojans are required to be inserted at safe places, which requires an attacker to understand the correct functionality and structure of the design. The next type is a removal attack. This attack aims to identify all the key gates from the locked netlist after performing logic encryption, and then targets to remove them from the locked circuit to unlock it. Unlocked circuit can be resold illegally to make illegal profit or insertion of malicious logic. The next type is called a SAT attack, which formulates a SAT formula and then the SAT solver generates an assignment to the distinguishing input-output pattern, and this DIP is formed to the activated functional IC. This keeps on going as long as we are able to eliminate the wrong key combinations till no new ones are performed or found out. So the question is how to defend against such cyber attacks. One of the ways is to have an enhanced locking approach with lightweight AES, Advanced Encryption Standard, for functional obfuscation of DSP based IP cores. An approach for designing several IP logic obfuscation blocks that include strong security features. Additionally, this could be augmented by adding a heuristic driven optimization framework to generate a low cost obfuscated netlist. And finally, the goal is to have enhancement in security in terms of the strength of obfuscation. So as we see, this algorithm was proposed in the paper cited below, where we have an optimization module or a PSO DAC based optimization engine that comprises of 4 major steps, which is initialization of the particle swarm, followed by evaluation of the cost, updating the local best and the global best, and then finally upgrading the velocity and swarm position. Now this keeps on interacting with the IP functional locking process, which is first to generate a random variable mu, and then generates the gate level structure post high level synthesis based on the particle position, and then inserts the ILBs at the outputs of each functional unit based on the value of mu and AES. of reconfiguration of the ILBs. So as I said that these ILBs are all reconfigurable and they do not have a fixed structure or architecture, and I said that this is possible because all the keys are actually coming through a different module which dictates what will be the actual structure of the ILB. So for an attacker to actually remove an ILB is literally impossible because it does not have an idea of how the ILB structure actually looks like. So how this is reconfigured is as follows. I'll take you back to that slide. So what typically happens is, if you see in this figure, we have the green block, which is a functionally locked netlist in a synthesized form that comprises of the ILBs, and in these ILBs the key values, which is k1 dash, k2 dash to kx dash, are all fed through a custom AES structure. Okay, so this custom AES structure comprises of the key inputs, which is k1, k2 till kx, and whatever output the AES generates, okay, based on that output the key values are reconfigured, which is resulting into the reconfiguration of the ILB structure. Okay, so the ILB structure is basically now dependent directly on the output of the AES, okay, which is again dependent on the fixed secret key of the AES, which is unknown to an attacker. There are some keys which are also fed directly without passing through the AES. So technically speaking, only the subset of the keys are passed through the AES. How this helps? This is actually helping in making the entire obfuscated netlist or functionally locked netlist resilient against SAT. So the custom lightweight AES with fixed secret key is integrated to a subset of function locking blocks in the obfuscated netlist to prevent an attacker from determining the inputs from the output. This also provides protection against removal attacks. Since the subset of ILB structures are reconfigured depending on the AES encrypted output, the number of possibilities also increase with the number of the key inputs that keeps on increasing, fed to the ILBs through the AES. Therefore, the attacker would not be able to identify the reconfigured ILB structures. So finally, I would like to conclude the talk by stating that the future of C system and IoT design, or cyber physical system design, autonomous vehicle design, is all about energy security trade-off. And I hope that you found out this talk to be useful. Thank you so much.